So, real pleasure to be here today. I'm Kyle. This is Amber. You remember the joint choreography that we practiced?
Oh,
yeah.
For the stage.
No. And we're going to be talking about troubleshooting unstructured data with embeddings. More specifically, I'm going to kick it off by talking a lot about all the different embeddings use cases at Etsy, and there are quite a few. All across search, image-to-image search, a ton of different things before I pass it off to Amber to talk about LLM observability. But let's kick it off. So I want to start by talking about ML at Etsy in general, because we do a lot of it, and we do a lot of it at massive scale. So these are some stats from like the last Black Friday, I think. It might have been 2 Black Fridays ago. But we were basically processing over like 280,000 requests a second, which is 11 gigabytes a second for us of feature data in real time in our machine learning platform that serves search, ads, and recommendations. So when I'm talking about embeddings here, we're talking about lots of data, lots of requests, and lots of infrastructure. But unstructured data, just like it's everywhere probably at your companies, is also everywhere at Etsy. If you look at an Etsy listing, it has a description, it has a title, a bunch of other information there, reviews, and that's just for a listing itself. We also have shops and other data that's unstructured all over the place, the images. So we deal with a lot of unstructured data that we have to make sense of and incorporate into our machine learning models. So we have embeddings in our, basically all of our ML workflows. First pass search, so basically an initial search. If you're typing into Etsy, we first go off to fetch a set of possible candidates from a search index. We use embeddings for that. We have embeddings as features in our ranking models for second pass, things like second pass search. And we also have embeddings for images, if we're doing image-to-image search or using images for use cases such as trust and safety, flagging fraudulent listings, etc. We even use embedding representations for some of our structured data. So here just highlighting that, like, you can also, oh, I turned it off.
Because it's my time to speak? No.
Yeah, I think so. I think I clicked it. There we go.
Testing.
Yeah.
Does this one work?
Does it? Yeah. In that case, I'll just do this. So we also use embedding representations for our, basically auto-encoding data that is structured about our listings and users. It's not just our general unstructured data, such as text and images, but we can even use embeddings to represent similarity between different users encompassing all of the information about them, from structured to unstructured. So a lot of different things going on. Here's an example of all the places that embeddings exist within our search workflows. So we start with one there. You're searching on Etsy. First, our orchestration system will go off and convert that query maybe into an embedding using an embedding model, and then it'll send it off to an approximate nearest neighbor search, which is an embedding index. That will fetch some possible candidate listings, say like 1,000 listings that we think might be a good fit. Then we'll send those off to our feature service and fetch features for them. Some of those features will be embeddings themselves. So for a listing review, we might have an embedding. We need to get all of those different embedding-based features for all of those different listings. Finally, we'll send that off to our ranking model, which might also have embedding layers in it. So we might have to load those into memory using embedding features, make predictions, rank those listings, and then return them back to the user. But the fundamental point here is that embeddings are everywhere and only increasing in their pervasiveness. That's a good word. Embeddings also power our listing-to-listing search. I included this slide just because this GIF is really cool, I think. And if you don't have the Etsy app, you should download it, start buying lots of stuff, tell all your friends. But the image-to-image search feature is also powered by embeddings. There's a great article on it. I'll talk a little bit more about it in a sec. But there's a great article on it on Etsy's Code is Craft blog. I want to get a little bit more specific, though, and not be purely vague, and talk about approximate nearest neighbors for our first patch search. So if you remember earlier, that was that initial fetch of listing candidates that needs to be very low latency and needs to fetch from basically all possible listings at Etsy. So we're talking a huge scale, and that's why we use approximate nearest neighbors here. So ANN search, it's a very, very popular topic at Etsy and in the industry, but it basically allows you to perform a nearest neighbor search across like massive scale, low latency without hugely compromising the accuracy of things like k-nearest neighbors, which would be an exact similarity. Some examples of libraries used, like Feist is one of the most popular ones, the Facebook library, but very similar to a KNN search, except it's approximate, so it's not going to be exact. But it lets us search across a massive amount of data. So an ANN search example using images would be something like this, where we have a image data set. We index all of the items in that data set based on their embedding. So every item is run through a model, gets an embedding, and then that embedding is indexed. When we query, what happens is we take this image here, also convert that to an embedding, and then run a search across this entire data set, which highlights similar examples based on their similarity within that latent space. So maybe some of us know this already. But we can use this for a ton of different things. So maybe we have a recommendation use case where we want image similarity. You upload you're looking at a listing, you want to see similar listings. We can use it for that. We can also use this for search where, like I was talking about earlier, you type in a query, we can basically take embeddings from multimodal scenarios, maybe they're generated from LLMs, whatever, and recommend similar items using that. There are a number of real-time ANN use cases live currently at Etsy using a number of different tools, actually. Here's a more detailed architecture. I'm not going to go too deeply into all of the technologies here, but this just kind of outlines everything that happens from a single Etsy web request to one specific type of ANN index at Etsy using Google's Vertex matching engine. So we have basically embeddings models trained on the daily, and rebuilding these indices that our search orchestration and ML model serving tools can use to essentially fetch nearest neighbors and then pass them off to a ranking model to be scored. Of course, we can't have all of these different embeddings without thinking about how we monitor and evaluate the actual quality of these results. Embeddings are a bit more challenging to reason about when it comes to monitoring. And this will be a good segue into Amber's talk, of course. But we've probably all seen something like this before. This is from the Etsy article that I mentioned earlier. The link is there in the corner. I believe you'll have access to the slides. If not, well, hit me up. This plot just shows a random sample of 1,000 Etsy images and the embeddings reduced to 3 dimensions so we can actually plot them out. So there's different kind of groups labeled here that were probably arbitrarily decided. For instance, we can see bags and purses down there in the corner have been clustered together based on the similarity of their embeddings. But that's not really a useful way to go about things at scale. We need to have labels for these things. So this is also from a recent article that we published. But basically what we did is we took some of the taxonomies that Etsy has and applied them to the embeddings that we wanted to classify. So these specific labels helped us evaluate the quality of our embeddings. Basically, we now have something that we can use to determine the accuracy or performance of a specific embedding technique or data set. And so obviously making anything supervised makes it much, much easier to reason about. We also perform some daily evaluations of our embeddings. For instance, for those search use cases I was talking about, on the daily we have jobs actually that will build an ANN model, build a KNN model, and then compare the two. So essentially we can evaluate the precision and recall at k nearest neighbors, comparing those two, where our ANN maybe has almost perfect recall at k, or near perfect recall or precision at k. And that's kind of the trade-off that we're making here between accuracy and latency when we train these models. Challenges, widespread of course. Embedding quality is relative and use case specific. High-level metrics don't always capture what we're trying to get at in regards to embedding quality. And it's really difficult to visualize and categorize embeddings in a way that is sensible for us. And embeddings are only becoming more pervasive as we introduce more LLMs to workflows and add different and new ANNs. And that's probably a great segue into what Amber will be talking about.
Thanks, Kyle. All right. So thanks, Kyle, for talking about embeddings and how they look at Etsy. We're going to talk a little bit about LLM observability, so large language model observability. This is very similar to ML observability or monitoring your models in that post-deployment production workflow. So what do LLMs look like in production today? So in addition to some of the examples we saw with Etsy's use cases, the most, I would say the fastest growing use case we're seeing is around prompt and responses. I know people have been seeing a million articles about LLMs and the progress that they're being made on. So this is a common example we're seeing, being able to have a question response system, either going directly through an LLM like ChatGPT or having an agent involved. And a majority of the conversations we're having with customers are about, can we implement these in production and have faith that they're going to make good decisions? And it's really hard, right? We know every time someone kind of trips up ChatGPT and writes articles about it, we know that these errors do exist. 46% of our customers that we've spoken to say that they are worried about inaccuracies if they deploy these models in production. That's obviously not going to stop the want of putting these models into production because of the time saved, because of the money that could be made by implementing them, and also just being able to free up people from customer success, from marketing. These can be used for personalization. So we've seen the endless possibilities with these use cases. But all these things are valid. They can absolutely hallucinate. They can have inaccurate responses. And they can just be bad prompts. And so what we're seeing kind of be the solution to this is through monitoring embeddings. So not just for prompt and response cases, but that's the one we're going to go into more detail on, but anything from search and retrieval, like Kyle was speaking about, to even classification and regression models also tend to have at least one embedded feature. But if you take a prompt and response, you can either combine them together and make an embedding. You can make an embedding of the entire data set. You could have each prompt, each prompt and each response have their own embedding. And then you could start tracking them through space. So here's an example of if you have prompt and responses. So what you're going to do is you're going to have these large embeddings. So think of the image that Kyle showed you of, one of these clusters could be purses. You would have this high dimensional representation, and then you would use a dimensionality reduction technique like UMAP to project the data into a space that we as humans can interpret. And so we're keeping important information, and what we start to see are patterns that emerge with these clusters. So cluster 1, we might see, all these reviews that we're getting or all these responses we're getting are in Spanish or a different language. Okay, we have one cluster here that uses some harsh language, and maybe these are impolite responses. And maybe they're just completely inaccurate. Or some of the responses of, I can't help you with this now. Responses that just aren't that useful. So the next step is starting with monitoring. So you want to be able to monitor drift. I know there's been some talks on drift evaluation for ML observability. So the same way that we try and evaluate how traditional models are doing in production, you might have a baseline, which is your training data, and you might have a production data set. So the same way we look at distributions and see how much those distributions have shifted, we measure that distance. So in a similar way, we can measure embedding drift. So if we look at a baseline cluster, so let's say we train our model, this is the data we train our model on, we put it in an embedded space, and then we have production data. So we have current data that's coming in, the data that's actually we're getting from our customers every day, and that's a new distribution. So if you see that the space starts increasing between what you expect and what you're actually getting, this tends to be the first inclination that there's something wrong with a large language model in production. And once you know that something is starting to drift, whether it's a traditional drift, a concept drift, or an embedding drift, the next step is to look into evaluation. So drift is great because you don't need the ground truths, you don't need the actuals back to see how good your model is performing. But once you have those ground truths back, it's critical to add them in so you can see exactly how your model is performing. So user-provided feedback, for example, like when you're given options on Etsy, if you actually are able to provide like 5-star ratings for the service you're getting, that's very helpful for them because then they get direct feedback on how their model is doing. Task-based metrics like translation or LLM's OpenAI evals or traditional metrics, also a great way of doing evaluations. And then now we're even seeing LLM-assisted evaluations where these large language models are starting to evaluate other large language models. So the possibilities are just getting wilder and wilder. So now that we've seen we can have prompt and responses, we can create those clusters, we can see what's in those clusters, now we have evaluation scores. So if we're using the OpenAI evals library, I highly recommend this library if you're looking for comprehensible metrics that can be applied to large language models. This is great. But what do you do once you get a poor evaluation score? So if you get something like 0.1 or 0.2 and you have a certain threshold, so let's say your threshold's 0.2. So you want to look at cluster 3 a bit more closely, then you'll have to do some analysis. And that can either be done by sending that alert to a machine learning engineer on the team or SRE or someone on the team that's going to look into that data a bit closer, or you could send it to another large language model. This is kind of the area we're headed, right? We have a separate large language model to at least do the first pass before an engineer then has to take a look at it. If you've played around with ChatGPT, you've probably seen that the more information that you give ChatGPT, the better calls it can make and the better responses you get. So if you have something that at the first pass wasn't that great, you have a second LLM that's most likely trained on a different data set, so there's no data leakage, then you can see what they suggest, and then maybe you have someone in the loop that can just confirm that. So it tends to make processes that engineers, customer service, customer success engineers are doing day to day, makes their whole process much easier. And depending on your use case, the third step, the root cause analysis, will look a bit different. But for prompt and responses, what we see is the most common is there's two options. You can either ask better questions or you can try to give better answers. So you're either doing the prompt engineering, you're looking at the kind of the prompt layers that are involved, and you're trying to ask better prompts. Or you can be on the side of, okay, the answers are terrible. The responses that these users are getting, they're not happy with them. And so that really involves either fine-tuning or retraining of the LLM. And so once you know these are the problems, you can figure out who on the team is most equipped to handle them. And like I mentioned before, just because prompt and responses and LLMs have the biggest uptake in use cases that we're seeing in production, there's still going to be embeddings for searching, for retrieval, for ranking, computer vision, NLP. All these are going to leverage embeddings, at least in one feature. And it's important to have an observability tool in play so that you're able to monitor them through space, because these are very large models and there's a lot of data to look at and to think about. If you're curious on how this would look for your use case, you can either sign up for a free demo. Arize has a free account, or you can just come see me afterwards and I can show you what it will look like if the Wi-Fi allows me. Arize also has an open source offering called Phoenix. So if you're more in that dev space and you want to work from a notebook, we do have an offering for our embeddings. So the Arize platform will track any use case, has a lot of additional features, but if you're purely interested in tracking embeddings, we do have an open source option. And here you can even see how this three-dimensional UMap, so this is a projected view, would look, and the isolations of individual clusters. All right, thank you. You were fast.
Classic.
All right, any questions? Yes.
So the question that I have is about how you actually measure the distance between this prediction and the latency.
Sorry, could someone get him a mic? I think we have two mics roaming around now. Yeah, they probably weren't prepared for us to finish. We finished early. Perfect. Thank you.
Thanks for the presentation. The question that I have is about how you measure the distance between two distributions in the latent space. So basically, you have a drift, right? And you want to measure the distance between two distributions. So how do you actually measure that in your framework or in general, right?
Okay, so I think I understand. So you're asking about like how do we actually measure that drift in embedded space?
In the distribution, right? So
Yeah.
assume that you have two Gaussian, so distribution, and you want to measure the distance, right?
Yep.
How are you going to do that?
Great question. So we first do, like for the Arize platform, we first do the dimensionality reduction technique. We use UMAP. We actually have some modifications on UMAP to do that reduction technique, and then we measure the distance either with a distance like a Euclidean distance, so a physical one, or a magnitude like cosine. And that's really just up to teams. The same way we do like traditional drift, you can use KL divergence, you can use PSI. So once it's decided within a team what they care about, then it's deciding a threshold for them. So we do automatic thresholding, but really it depends on what the team's looking for. And if they're looking for kind of the global data set, because some will put an entire data set into an embedded space, and some people just care about the local clusters. They care about individual local clusters and how those are moving. So we use the centroids, and then we track that distance. But some care about drift, and some just care more about performance. Like I don't care if these are drifting, that's totally fine. I just care if we're losing customers because of it. And so a lot of that is just up to teams, but we give them the flexibility on if they want to monitor for drift first and performance, and then really just point to where the problems are in the data. Does that answer your question?
So thank you both for your very insightful talks. I have a question for Kyle regarding the user listing embeddings. So the way I understand embeddings is that for text data, for like image data, you have the neural networks kind of form these large dimensional vectors that pick out certain features that might not be always like human understandable. But for like user data, for example, it is a little bit structured. So I'm just trying to wrap my head around how you create embeddings for those, and if they're like 720 dimensions in length as well, or if it's normally like user this name for like John Smith address, like just if you could kind of shed some light on that.
Yeah, for sure. So there is a paper that came out, I forget when we started doing this for search specifically, but they're called VPCG vectors. Look up the implementation, but I believe the idea is kind of the same thing you get with like principal component analysis or something, where you're almost doing dimensionality reduction on a ton of different features, some of which are probably embedding based themselves, to get a lower dimensional representation you can use for computing similarity. That paper on VPCG vectors goes into more description on how they actually leverage them within a specific search, like the search ranking process. But it's more around like I believe the dimensionality reduction and similarity than it is around just like representing things as embedding. Yeah, no problem.
Question for Kyle again. What model or type of model are you using to generate the image embeddings at Etsy? And are you doing any kind of segmentation prior to that?
Got it, yes. It took me forever to find you there. I was like, where's that voice coming from? Yeah, sure. So there's a bunch of different models that like generate embeddings depending on the use case. They're almost all, some of them are pretty standard like neural networks that just take out the embedding layer, like basically just trained in-house on our text data, and then we take that embedding layer and make it reusable for different use cases. Most of them don't use like generative AI or LLMs today, although we're kind of moving in that direction. But I think the Code is Craft article talks a little bit more about some of the specific like transformer-based structures that we're using to actually generate the embeddings themselves. But they're all pretty much, I think like most use cases, they're like models that are fine-tuned in-house on our data, and then embeddings are taken from that.
For images?
Huh?
For images or text?
For both, I believe. Yeah.
Thank you.
Hey, quick question on the embedding drift that you talked about. So I'm assuming the data is stored in a vector database somewhere, and if there is a drift, are we re-indexing based on the fact that there was a significant shift from the query distribution to what data exists in the database? Like, isn't that a very expensive operation every single time you notice the drift?
Oh, that's a good question. Yeah, so and depending what companies want to do, so you can sample, like that's an option, but a lot of teams just want to know, a lot of times care more about the overall drift, so the global drift between a training data set and a production data set. And you can run that at any time. So one of the reasons we use UMAP is because it's very efficient. It's in like the neighbor algorithms, but it is the most efficient, and our modifications make it the most efficient. So it is computationally dense compared to, if you have like structured use cases, but it's the fastest, most efficient way we can do it. And then depending on how often you retrain your model, you only have to, see where everything is for training once, and then maybe you look every, maybe even every week to see if that drift is happening. For a lot of teams, the ground truths are going to be a bit more important, so like that performance aspect, but it's actually not as dense as you think. Like I can run the calculation on this Wi-Fi, so in case you understand.
Hi, I have a question. So just have a question in general regarding to customized embeddings. So let's imagine there's a use case for like a dating app. So for user put like a bio, say, I hate going to the restaurants, I hate wine, and I hate travel. Compared to another sentence, I love going out to restaurants, I love wine and love travel. And if you put these two sentences to OpenAI embeddings, the similarity is actually 0.92%. Like there's only 0.08 difference from these two sentences. So they are very similar within the sentences, but they are so much different if you want to do like a matching algorithm based on these two sentences. So how can you solve this problem in production? Because I guess this is very common, because you cannot capture the nuance within these sentences using embedding models.
Yeah. Is that a question for myself or Amber, you think?
Do you want it?
So in embeddings in general?
Well, I think for you, Kyle, like the nuances don't really matter in a lot of use cases. So nuances are tricky, but like I think for managers and everything, like when they're looking at like profitability, KPIs, nuances don't play as much of a role. I think that I see that more in like research and like the distinctions. But yeah, if you have different thoughts on it.
Like, I guess, the high level, I guess, would be like that people are just, as we see in the industry, just training bigger and larger models to try and capture that nuance. But it comes down to your use case in regards to what nuance is important. So like maybe that nuance is important for like certain recommendations, or maybe for another use case, it doesn't matter at all. And that's why we kind of have the fine-tuning process of these are my embeddings for my use case that are good for search and trained on some supervised target that I want them to be good at. And I don't care if those two sentences aren't similar in my data set, but I do care if these other two sentences aren't similar. I think it's just gonna come down to like the trade-off between how much you're willing to pay to capture as much nuance as possible versus how much you're willing to like kind of chop things off to focus on your specific use case and make things as optimized and small as possible. But in short, like all things, I think it's a trade-off.
Okay, thank you.
Yeah.
Question here. You talk about drift and embeddings by looking at the average vector and how the distance between average vectors kind of shift. There's another kind of drift that I'm curious about if you thought about it all, and that's where the clusters themselves start changing. I think an example at Etsy is there can be a lot of unique, very unique kind of products that defy classification. And so the embeddings are very useful to say, oh, these very unique items are more similar to each other. But one aspect you might look at is how do customers respond to these? Like they like this, but they also like that. Maybe that makes them more similar. So that might change if customer behavior changes, right? And you might want to track how do customers treat these, and that might change how they cluster. So as a source of drift, do you look at somehow able to track how your clusters themselves are changing with time?
Yeah, absolutely. I think that's a good point, right? There's like comparing like two different like current data sets, but then there's also like comparing today versus yesterday. And so I think the simple answer is we just like are kind of looking at past baselines and computing similar kinds of drift in regards to how much different is this data distribution from yesterday's data distribution in regards to purchases or clicks or other like customer actions kind of thing. But I think the fundamental change there is what the control is and what we're trying to, and what we're comparing against in regards to what's currently going on.
Yeah, and just to add to that, like being able to change out that baseline is really important. So like you're changing out baselines, you could change out different versions of data sets, because if you're looking for the things that you're talking about, you only find that by doing a lot of comparisons. And then normally they start on like globally, like is this data that I got yesterday different from like last week? And then looking specifically, like the root cause analysis part is seeing like, oh yeah, like these are different kinds of hats and things that are being made now. And then that is really the root cause once you get to the local area.